Okay, today is May 8, 2024, and here is the schedule of classes. Okay, here's the schedule where we are on May 8th. Today we're going to have the lab number 8, the diode, and first hour we are going to continue on special relativity, okay? Let's not forget that we have an exam next Wednesday next week, right? And here are my notes. Third, a break. That's 05/08/24 Wednesday. That week number 15. No, week number 14. Week number 14. Partial exam 3 is in 7 days. 7 days on May 15, 24. May 20, 15, 24. Chapters 22 through chapters 22 through 26. And you have the list of sections here. Let me display that for you again. Yeah, we already have it here. One section of chapter 20, right? Plus one section and 20 point whatever. I'm going to get that for you. 20.5 and section 20.5. Right. In chapter 26, we skipped that. Let's say we did the human eye. Okay, and then we didn't do the other ones. Skip for now. Skip, and skip for now. And then we also have the labs. And let's see. Okay, I didn't write that down here, right? So let's see there at the top, exam 2. Exam 2, okay, right here. Lab 1 and 2, okay, good. So now we are going to have the labs, lab 3 through to the one that I corrected. I just corrected lab number 6, I believe. Let me go there. Lab correction. Yeah, I correct lab 6 and posted there. Let's see if I have done. Okay, I haven't done that 7 yet. Okay, good. So labs 3 through 6. Okay, I posted the correction to report the report of lab 6 as PDF format. Okay, and let me show you there in your here you go. Okay, group 1, right? Here you go. Here's the correction of lab report 5 and report 6. They're in PDF format. Remember, I told you that? They're in PDF. And that's for group 1. Group 2, we have a similar situation, 5 and 6, right? And group 3, only 6. Let's see, did I have 5 here? Yeah, 5 is on the other folder. Okay. That's the situation here for post correction of the report of lab 6. Okay. For exam 3, partial exam 3 in 7 days. Okay, plus, right? And labs 3 through 6, 4 different labs. That's the situation. Okay. That's the list.
Professor, the total exams are what? 4? 4 exams.
What's the question?
The total, because we're gonna do exam 3, you're saying soon. Is the last exam 4?
No, it's the final exam. There are 3 partial exams. I'm gonna write it down for you. We have 3 partial exams and 1 final exam. Okay, so it's 3 partial exams and 1 final. Total, yes, total is 4. But don't forget, 3 of those exams are partial, whereas the final exam, all the material, cover all the material in the semester. Okay, clear? And you go and then when's going to be the final? The final exam is going to be May 29. Okay, labs. So let me put here labs, lab 3 through 6, right? Here is lab 1 through 2, labs 1 through 2, labs. That's the material, and here all chapters, everything. Let's put not instead of all chapters, let's put everything, because we still have the labs as well. We are writing here in the schedule. Any more questions? So just like before, I want to continue with the lecture, and then for the first hour, and then the remaining of the time, we will do the lab. Okay, here all the material, and you should have all the recordings. I posted, right? I posted the links of all class recordings for covering the material for the exam. Posted the links of all class recordings covering the material for the exam. So it's in there. You have it there, okay. And let's continue in special relativity. Relativity. What we are covering time dilation, okay? And the idea of time dilation is the following. The result that we get, right? I'm going to give you the final result, and then I'm just going to review quickly what I did last time. The result for time dilation is the following. Okay. In a referential that the light clock is relatively at rest. Okay, it will measure a period of full oscillation of the photon as being, let's go back here, right? Previous class. This one right in here. Okay. V. And then let me just give a little bit introduction here, right? Like consider two referentials, A and B, with A at rest with respect to us, right? With respect to us, and B moving with respect to A. Okay. Someone else is coming. Let's see. Referential B has a clock, a light clock that I will light clock C. Okay. The idea here is to take time measurements from of this clock C from each referential separately. Okay, that's what it is. The period of clock of the light clock C measured. Don't forget, consider two referentials, A and B. Here you go. A is at rest with respect to us. Okay. Here you go. A is at rest with respect to us. B is moving with respect to A. B is moving with constant velocity. With constant velocity. Okay. So it's going to be like that. Consider the two referentials. Referential B has a light clock C, like that. We want to take the period of clock C from each referential separately. Okay, separately. We want to take the period of clock from each referential separately. Okay. An observer in referential B, you know, has the clock at rest, right? With respect to him, right? Respect to him. The so-called proper referential. That's a very important idea here. Proper referential. So if the clock is at rest with respect to an observer, so we say that the referential of the observer is called the proper referential. Okay. This observer measures a period period of the clock, right? The period of going back and forth from one mirror to another one. I want to remind you of that, right? Let's go. Here's the light clock. Here you go. Here's the light clock. Okay? Imagine this, the light clock has a photon here and two mirrors that traps this photon in between them. And the photon keep on bouncing back and forth. Can you tick tock, tick tock, tick tock? Okay? Like that. That's the first frame, that's the next frame, that's another frame. See, the photon is moving. It goes back and forth. The period of the clock, of the light clock, is going to be the round trip back to the lower mirror. Okay? And it's very important that we come up with a notation. The notation that I like to use, okay, is the following. The idea here is to take time measurements, the period, to take a measurement of the period of this clock from each referential separately. The period of light clock measured by an observer in B, the proper referential. Okay, we calculate. It's easy to do that, right? It's just what I wrote that before, and that's easy to calculate, right? Because it's just the distance, the length, right? The length between the distance between each mirror is d. The round trip is going to be 2d. The speed of the light is c, according to the postulate of Einstein. The speed of the light is c, right? It's going to be something like that. This knot here means that is the time of the proper referential. My notation, the one that I like to use, is this one right here. Okay? And what does this notation mean? This notation means the following. The period of clock C with respect to an observer in referential B is twice the distance between the mirrors divided by the speed of the light. Okay? That's the proper time. Not proper time, right? Proper, if so-called, so there is proper referential here and proper time here. And then last time I calculated for you. Let's do that again. Okay, the measurement, on the other hand, the observer in A, on the other hand, measures a period of clock C as being different because in his referential, the photon is displacing a longer distance, right? Okay. Namely, in B, in referential B, the photon displaces a distance to D. Namely, I'm going to do like that. We go in referential B, whereas in referential A, the photon displaces a distance. The observer, right, in referential A, the observer, whereas the observer in referential A sees the photon displacing a longer distance given by going back to our I'm gonna get that right angle triangle, right? let's see. I'm gonna get this one here. By. Here you go. Two diagonals, right? Two diagonals, the distance of the two diagonals. The distance between the two mirrors in the light plot, the velocity of the referential B with respect to A, and the period of clock C as measured by the referential A divided by 2, because it is half of the period, right? Going back again to our drawings, right? You go. I have it right here. Here you go. This one right here. This is D, right? And this is VT divided by 2. And T of C sub A. Okay? VT sub A divided by 2, because that's half of a period of the clock. That's the full period of the clock. And this one here I should put to be consistent. I should use it as a capital D to be consistent with our notes, right? Here you go, capital D. Okay. That's the distance. Distance moved by the photon as measured from referential A. Okay. Okay, because the distance is longer, the period of the clock C as seen from A seems dilated, right? Or longer. That's why it's called time dilation. Okay, so let's continue here with the. Okay, so here you go. The speed of the light, according to Einstein postulate, the speed of the light is constant. And this is, let's see here, this is not supposed to be c squared, this is supposed to be c. I just noticed that, yeah. TCA, okay? The square comes afterwards. Because we have the square root here. Because the distance is longer, because the distance, an observer, because the distance the photon moves with respect to A is longer, the period measured by A will seem dilated or longer as well. Right? Let's see now what we have to do here. Then is the idea of time dilation, right? So I'm going to continue with this equation. I didn't derive it for you. Okay, I'm gonna pass the number 2 to the other side. In the next step, I will square it. Okay, here is gonna become square as well. He's gonna become square as well. He's gonna become 4. Okay. And let's continue. I'm going to distribute the squares in this one right in here. Like that, divided by 4. like that. Okay, this term here is greater than this one because the speed of the light is the largest speed that you can have, fastest, not the fastest speed you can have in the universe. Okay, we're gonna pass this term to the other side. Okay, what I'm trying to do, we are trying to solve for TCA. Okay, trying to solve for TCA. And we can go the next step here. I'm going to put TCA in evidence, TCA divided by 4. I'm going to put that in evidence, like that. Okay. In the next step, here you go. I'm putting TCA square divided by 4 in evidence. Okay. And now we can solve for this one. I'm going to highlight it here. This is the equation here that we end up having, okay? That's the equation here that we end up having. So next step is going to be 4 here. Oops. 4. And this one is going to be divided. I passed the 4 to the other side, so I don't need that anymore here, right? And solving for TCA, we get equal 2D divided by, I don't want that both faced, have the square root here. Okay, like that. TCA. But there's more. There's more. I can do another simplification here. What I'm going to do next, I'm going to put C squared in evidence. Okay, so the equation is going to look slightly different. It's going to be easier to understand. V squared divided by C squared. Don't forget, I'm going to write that down, TCA stands for period of the clock C as measured by an observer in referential A. Okay? And we can do the same thing for the rest, right? TCB stands for period of clock C as measured by an observer in referential B, right? And what else? There's one more here. Oh. V B with respect to A stands for speed of referential B with respect to A. Referential A. Okay. The advantage of this notation is that it allows you you don't lose information. Okay, so here, that's the advantage of this notation. You don't lose information from in the process. You go, and then I can. What I did here, I took out the C squared from the square root, right? I'm going to do like that. You go step by step. So I am completely So that's why I'm rigorous. So I don't have it here. Why am I doing that? You're going to see why I'm doing that very soon. Okay. So that's what we end up having. Okay. Going back to the definition of TC with respect to B, right? See, 2D over C, right? So we're going to replace right in here period of the clock C, capital C, with respect to referential B. Okay. And remember that this one here is the proper time, right? Which the book calls, according to the notation of the book, is delta T naught. And this one here, it's not the proper time, it's the other time there. And the book calls it just delta T. Okay, that's the relation between my notation and notation of the book. Here the book calls VBA, you just call B, according to the book. This one is going to be V square, according to the notation of the book. I'm going to put those two notations side by side. Here you go. Book's notation. Book's notation. Okay. My notation. The proper time. Proper time. My notation. It's going to be like that. Is, this is square root here. I'm going to put this one, let's see, a little bit higher, right? I'm going to put it right here. Or maybe before. Okay, good. I put it like that, better. Organize it. Okay. Oh, let's see. And now we're going to plot. Okay, but one more thing, right? The ratio appear, the following ratio appears, the ratio, let's see, the ratio like that. Let's write that down. The ratio 1 divided by that appears very frequently in relativity. Appears very frequently in relativity. For this reason, we give it a name, the gamma factor, or like that, gamma equal to that. And our relations, which by the way, is always greater than 1, okay? Always, remember this number here is less than 1, right? When you subtract 1 by a number less than 1, this one is going to be less than 1 as well. 1, and then you take the square root of a number less than 1 becomes less than 1 as well. 1 divided by less than 1 is going to be greater than 1. Okay? Gamma is going to be greater than 1. So let's here write book notation, my notation. It's going to be gamma. Right? Gamma. Every book, calls that ratio gamma. I have never seen a different name for this ratio. Okay? Book's notation, my notation. So this thing is always going to be greater than gamma. And if we plot that in Excel, let's do that. $9.30. Okay, view freeze pane. Panes, V over C, right? I'm gonna put that V over C. There's no unit there. If let's say the object is initially at rest, right? I'm here. I'm going to put let's see. Let's plot just gamma. Let's plot just gamma. Gamma has no unit. Oops. What's going on here? Format. Okay, so okay. Like that. Okay, gamma is gonna be 1 divided by square root of 1 minus this value here, right? So gamma is going to be exactly 1 whenever the object is at rest, whenever the referential B is at rest with respect to referential A. Now, as it starts moving, let's say, 1/10 of the speed of the light, right? 2/10 of the speed of the light, and so on. Look what happens to this gamma factor. Let's do 0.05 so we can get more data here. Okay. So here we have a relation, at rest with respect to the speed, at rest with respect to referential A, 5% the speed of the light, 10% of the speed of the light, 15%, and so on. As we approach the speed of the light, this gamma factor keeps on increasing. What does it mean? It means that the time that the observing referential A C for the clocking B gets dilated. Gets dilated means what? The clocking referential B seems to be running slower, okay? That's how it is. The guy in referential A will have his own clock, and the other guy in referential B will have the other clock, the second clock, right? So he's comparing, the guy in referential A is comparing the flow of time of the clock in B with the flow of time of his own clock in A. And he's measuring that other clock to move slower than his own clock. The time is dilated. The time of the clock in referential B is dilated. Okay, we can plot that. Insert. If the clock is seen to be slower, to move slower, it means that the guy in the other referential you seem to age slower as well. That this one here. Oh, let's move it. 0.5. Yeah, that's how the gamma factor looks like. It's increasing, it increases asymptotically towards 1, okay? Here at 1, whenever the speed of the light of the spaceship is equal to the speed of the light, whenever the speed of the ship is equal to the speed of the light, this gamma factor goes to infinity. Okay, we can even go the next step, right? You're going to see that Excel has a division by 0 here. Okay? That's how gamma is plotted. I am going to, let's do a nice job here with this graph. And I'm going to copy and paste. Okay? I'm going to add also my chart elements, axis title, primary horizontal. That's going to be V divided by C. Okay? Velocity of the referential B divided by C. And axis title, primary vertical, right here. Gamma. Symbol. Like that. Bold faced, right? They have no units, right? I can even, I'm going to put that, I'm going to emphasize that by putting the number 1 between parentheses. Nor gamma, neither VC has any units whatsoever, right? Like that. Asymptotically. And I'm going to copy this guy. Snipping to, here we go. Run. Notes 2024. Why is not okay? Here we go. Plot gamma against V over C. Okay. Note C. According to the behavior of gamma, right? TCA will always be greater or equal than TCB. Okay. Subscript, greater or equal. What does it mean? This means that an observer in A sees the clock in B running slower. Oh, see, running is slower. Okay, that it means if B is at rest, they're gonna be equal, right? But if B is moving, then it's gonna be less than TCA. This means that no observer in A sees the clock in B running is slower. When comparing, running is slower when compared to his own clock. I like to call the other clock C prime at rest in A's referential. Okay. This also means that A perceive an individual in B as aging is lower than him, than another individual in A. Okay, that's what TCA greater than TCB means. Perceived. This also means that an observer in A, right? An observer in A perceives an individual in B aging is lower than another individual in A. That's what it means. Because, because TCA is greater than TCB, comma, we call this phenomenon time dilation. Okay, this is now imagine scientists back in the 1900s, in the early 1900s, trying to make sense of that. Is it possible that time is relative? That's what they were asking themselves. How is it possible someone doesn't age as someone ages differently when they're moving faster? Okay, that's what they were getting at that time. We can here you go here we can so let's say suppose that the period of the clock is 1 second, right? As the spaceship, right, as the other referential moves faster and faster, someone in A is going to keep on measuring a period that's longer and longer. Writing here around, let's go back to Excel. Writing here around the 0.55 the speed of this light. The other clock now will be measured to have a period of 1.5 seconds. Moving faster. Here you go, right in here, exactly 0.8. The other clock, instead of having a period of 1 second, is going to have a period of 2.23 seconds, 2.24 seconds, and so on. And as we approach the speed of the light, the clock in the other referential that's moving, the period of the clock in the other referential becomes longer and longer, right? Or let's say, becomes slower and slower. Time flows slower in that referential. Then the term, time dilation. Okay. So we have, let's take attendance. Any questions about that? Today is, okay, today's the lab. Today is the 8. Okay, right here. Insert, okay. Jacqueline, are you there? Hi, Jacqueline. Jacqueline is not answering. Oh, okay, now she answered, right? Okay, thank you. Next, Yorgo. Yorgo is here, right? Hello,
Yes,
Yorgo.
Professor, I'm here.
Okay, thank you. Paul Zapata. Hello, Paul. Okay, Fo is not answering. Let me put a star here for him. Norberto disappeared, right? And Vanessa.
Here.
Thank you. And Sky is here. Okay, thank you, Sky. Ashley. I don't see Ashley here. And Corina. I don't see Corina either. Let's see, 4, 5, yeah. And Paul Zapata, are you there? I want to give you another opportunity for you. Okay, let's take our break now, 9:45. Break from 9:45 a.m. to 10 a.m. And I see you soon. Okay? We are back here. Now. Okay, so now we are gonna go for the lab. Oh, don't forget, right? Today is gonna be lab number 8. Here you go, lab number 8, right? Lab number 8. 8, another non-ohmic element. Non-ohmic element. The diode. The diode. Go. Here you go. Non-ohmic element, the diode. Okay? And I will put a page break here. And what I need you to do, okay, upload. I'm gonna repeat what I said before at the beginning of the class today, right? I corrected the report for lab 6 and uploaded to your group folder. Okay, see PDF file. 2, report for lab 7 is due now. Okay. And that's basically that.
Professor, when is lab 7 do you said? Today you said?
Yes, that's right. Now the report for lab 7 is due now. When did we do the report for, when did you do lab 7? Let's see, we did last week, right? Yes, that's right. We did last week, and you're supposed to turn it in before the beginning of the next lab meeting. Okay, so it's, and this lab 8 will be due on 22nd, because next week, we're gonna have an exam, right? So here you go, let me write it down here, report for lab 8 is due, I said 22nd. Let's see here, my calendar. Yeah, the 22nd. 22nd, 24. Okay. Is due before the start of the next lab. Before the start of the next lab. That will be on August 22nd. Don't forget, we have an exam. We have an exam. What did I put it here? 05. Why did I put 8? Yeah, we have an exam next week. next week, that should be 05/15/24. Okay, and all the material that's gonna show up in this exam is listed here, including reports, right? The reports including the labs 3, 4, 5, and 6. Okay. Don't forget, I skipped lots of material, right? For chapter 26. And let me get my notes for lab 8 here. No matches. Lab 8. Let's see. No matches. Ay, 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 ay. Week 16. Oh, that's special relativity. Okay. Yo. Man, this thing takes so long to load. Huh. Why is that? Maybe I need to update my Windows. Every time my computer becomes slow here, that's because I need to update Windows. Let's see. Still loading, still loading. Oh, so slow. Okay. Dial, let's see if the notes for the dial is here. Okay, yep, right in here. That's my last year's notes for this lab. Okay, so ohmic elements. So what you have to know, we have ohmic elements, just like regular resistors. Okay, and you have no ohmic elements, flashlight bulb and the diodes. Okay, we in the lecture we do not cover non-ohmic elements. Okay, we cover non-ohmic elements only in the lab. Non-ohmic. Did you notice that? Non-ohmic elements only in the lab. Okay, so we didn't cover the theory of the flashlight bulb, of the resistance of the flashlight bulb. We didn't cover the theory of the diode in the lecture, right? All we are going to do is, to show you some actual experimental data so you can appreciate the fact that there are other types of devices out there in which the Ohm's law doesn't apply, okay? So we perform these experiments only to expose you to the idea that there are certain elements that do not obey Ohm's law. Not obey Ohm's law. That's why. Perform, right? Let me put between quotes here. Perform these experiments. Okay, Ohm's law, just like you have memorized, right, is something like that. V equal to Ri, which can be here written as the resistance is V over I. But for the flashlight bulb and other non-ohmic elements, this relation is changes, okay? It's not written down as V over I, but it's written down as delta V over delta I. Because, and this resistance here ends up being a function of V and I, okay? Not is a constant for a given resistor, for a given resistor. The flashlight bulb, nor the flashlight bulb, okay? Nor the flashlight bulb, neither the diode obey this law. But it obeys, but they obey, right? A somewhat similar relation. Okay, the resistance is a function of the voltage and the current, and instead of R equal to V divided by I, it's going to be delta V over delta I. Okay. Okay. Now, what's the diode, right? The diode is a semiconductor device that transmits current in a single direction. That's what you have to know. Can you remember that? That's what the diode does. It doesn't let the current flow in one of the directions. It allows the current to flow in only one direction. And I'm going to show you the illustrations, right? I need to show you the lab illustration, and I'm going to close this one as well. Lab 7. Raw data. So file videos with lab slides right in here. Okay, two diode resistors. Okay, here you go. So whenever you have the symbol of the diode or of the diode is this triangle with this line here. Okay. Now the LEDs is a light source that is also a diode. It behaves like a diode, and the symbol for the LED is the symbol of the diode with a circle around it. Okay. There are all sorts of diodes, LEDs out there in the market, and those devices are mass manufactured and they are very cheap, depending on the LED, of course, right? Depending on the LED. I have here with me, one. Let's see if I can get an actual LED for you to see. Well, there are some. I have the support here with 1, 2, 3, 4, 5, 6 LEDs. They are in this hole, in those 6 holes. And those LEDs, they emit light in the UV part of the spectrum. 375, more or less, okay? In the ultraviolet region of the spectrum. There are all sorts of packages for LEDs. Let me show you an illustration in case you do not know. Okay. Most likely you have already seen LED strips, right? LED strips, they have a special type of LED that we call surface mounted LEDs, okay? So let's see if they have, and they are very small, very flat. Let's see, and you see here now those LEDs, those LED strips, they are very popular nowadays. Those LED strips, especially the programmed LED strips, they started to be commercialized around 2010, 2015, okay? Before then, we didn't have those LED strips. We used to buy only LEDs separately, just like light bulbs. Let me show you, let's see if light emitting diode. Here you go. Okay, so here you go. Here's a picture of a light emitting diode in the bulb format, right? And they're housed, they have a housing here, this plastic thing around it, but the actual LED is this one that you see here with the two legs. Okay, I have a bunch of those LEDs here at home. Could show, okay, here you go. See that the bulb, in a bulb-like fashion, okay, that's how the LEDs started to be commercialized. I bought those bulb LEDs back in 2001, 2002. Okay, it was a UV LED. Most likely, I was one of the first scientists to start using UV LEDs in for actual experiments. Okay, let's see if they have now. They have all those lamps, right, made of LEDs. They're big lamps. Though these LED that you saw here, they're very small. They're usually 5 millimeters in diameter. Okay, and okay, here's another LED. It's a different packaging. Texas Instrument SNX 100 gallium arsenide LED. The packaging is called T018, transistor metal case. This one is the surface mounted LED. Okay, it's a very small device, the surface mounted. And those are, the surface mounted are the ones that are present in your LED strips. And okay, here you go. Those blue LEDs. And again, this one is roughly half centimeter, 5 millimeter diameter. Each one of those LEDs. You know, by the way, it was very difficult to develop blue LEDs. It was one of the last LEDs that we managed to develop and make it available commercially. Okay. Original blue LED. RGB systems. RGB stands for red, green, and blue. And we use red, green, and blue LEDs. Here are the curves, the spectral curves of the red, green, and blue. Okay? The wavelengths of them. You go, RGB LEDs projecting red, green, and blue onto the surface. And then we have white LEDs as well, which are the phosphor-based LEDs. Okay? If you go also in the Mauser website, Mauser Electronics website, they have all sorts of LEDs. Let's see if I can get the Mauser. I don't want the Brazilian one. Mauser Electronics. Must be this one. No, Brazil, no. Let's see if they have a link to the Mauser in the States. Mauser is a company that sells all sorts of electronic products, and they also sell LEDs, including LEDs. That's all in Portuguese here. There must be a way to get into the American website, but let's see if I can get LEDs. LEDs. See, you're going to see. Okay, here you go. Here, those are the surface mounted LEDs. Okay, this is one of the surface mounted. And technical data sheet. They usually has the measurements of this chip, this little chip. Let's see if they have it here. Let's see. That's the spectral distribution of the LED. This is a white LED. The white LED. You can see it has a broad band emission here. I just want to show you the dimensions of this device, but it's usually like a 5 millimeters as well as a square, is a rectangular device that's like roughly 5 millimeters, but it's a flat device, unlike the light bulb that you saw. Okay, so there are all sorts of LEDs, and those SMD LEDs are the preferable one for mass manufacturing devices, okay? For manufacturing. Okay, here you go. Okay, those are the dimensions, mechanical dimensions. And that's 2.8 millimeters, 3.5 millimeters. So it's less than 5 millimeters. Okay, it's less than 5 millimeters. And those dimensions are in millimeters. They should drawing not to scale. All dimensions are in millimeters. Okay, and let's take a look at the LEDs made of other packages, right? The ones that has the format of a light bulb. Oh, well, it's gonna take forever for me to find this one. See, they have only SMDs here. Let me see if I can make my search more LumiLEDs. Let's see, 3 LEDs, biver LumiLEDs, PCB SMD. Maybe it's this one. Nope. I removed the SMDs from. Okay. Let me see if I can find the other one for you. Okay, it's very good to take a look how those things look like in real life. I'll be back shortly. Found it. Light bulbs that I mentioned to you. That's how they look like. Let me stop sharing my screen so you can see a larger picture, right? They are exactly like a light bulb, right? A small light bulb. And they have two endings here. One has to be connected to the positive side of your battery and the other to the negative side of your battery. This LED is an orange LED, 5 millimeter diameter. Okay, so that's the type of LED that I started working and I was performing my experiments. And later on, I evolved to the smaller LEDs because they are more appropriate for mass manufacturing and for mass manufacturing devices. Okay, and then when we do the experiments, I use this type of LEDs with my students in this circuit. And let's, what I have to do first, right? I have to upload your lab reports, your data, lab data, raw data, lab 8. Let's make sure everything looks fine here. There's no. Okay, this one looks good. This one looks good. This one looks good. This one looks good. Yeah, this one looks good. And this experiment is going to be similar to that of the flashlight bulb. It just happens that the curve is going to be different. The VI curve, or we call it the IV curve for the LEDs, is going to be different from that of the flashlight bulb and different also from the resistor, right? But the circuit is similar. Two devices in series, one resistor and LED, and the other one an LED. Now, let's see here. Copy. You. Copy folder. Okay, and I will upload the lab reports for you right now. I understand that we do not have a group 2 anymore, right? Is that right, Vanessa? Is Vanessa there? You were in group 2, right, Vanessa? And now you're no longer in group 2.
Yes, I'm in. You
Okay.
assigned me to group 3 now.
Yeah, I assigned you to group 3. That's good. And Norberto disappeared, right? Let me upload just the report for group 1, the spreadsheets for group 1 and group 3. Okay. And can go ahead. Download the spreadsheet for lab 8 to your hard drive. Okay? And what we're going to use so what we're going to do, we're going in this lab, you will connect a diode, in this case an LED light emitting diode, in series with a resistor. So you can study how the current flows in this circuit and how the LED behaves, right? How the LED behaves. So the equipment, the list of equipment, I'm going to show the list of equipment as the devices start to show up. Okay, so here you go. Here's my, we start, let's see, we start measuring the resistance. Yeah, I didn't draw the What a shame. Yeah, I need a. Okay, the first thing that you do, and I need to open lab 8. Let's open here group 7. Here you go. Here's the spreadsheet, how it looks like, right? The first thing that you do, you measure the values of the resistance of resistor 1 and the resistance of the diode. That's what you do. Okay, so measure resistance of the resistor. Actually, you don't, okay, with a DMM, with a digital multimeter. So we start with this list here, list of materials. 1, right? Resistor. This one. Resistor between 30 and 100 ohms, just like before. Digital multimeter, DMM. Okay. Measure resistance of the resistor with the DMM. After measuring that, build a circuit with a resistor, with the resistor, right? The resistor and the LED in series. Okay, so next element here that's showing up is a LED. Okay, we're going to need a power supply as well. Okay, connect the power supply in series with the LED and the resistor. And when you do that, you're going to need black cables, black cables, usually with banana termination, and red cables with banana termination, and we're going to need also alligator clips. And by the way, you're also going to need the protoboard, right? Connect, let's say, build the, we're going to do the following here. Measure resistance, use, connect the resistor, here you go. Connect the resistor and the LED in series using the protoboard, right? And then you connect the power supply in series. The protoboard comes right in here, comes before the power supply. And the drawing looks just like that. Here you go. Power supply, right? Resistor 1, LED. Both the LEDs and the resistor are connected in series using the protoboard. Here's the symbol for the LED. This triangle that you see here in the LED shows the direction of flow of the current, okay? So current can only pass from the right to the left. If you connect the, if you try to pump the current on the other direction, the LED is going to prevent that from doing. Okay, so here you go. That's the whole circuit in series. So we have a red cable going from here to here, right? And then we have an alligator clip, one red cable, one alligator clip. We have the resistor connected in series with the LED using the proto board. And then we have a black cable connecting the, make sure you get the right polarity of the LED, okay? So usually the longer leg of the LED is the positive one, is the one that connects to the positive side of the battery. And the shorter leg is the one that connects to the negative of the battery. Okay, here you go. See two legs here, one longer than the other. That goes facing the positive side of the battery, and this faces the negative side of the battery. And we close the circuit. So far we have one red cable, one black cable, right? Let's put one black cable with banana termination, one red cable with banana termination, two alligator clips, One alligator clip goes on this side, the other alligator clip goes on this other side. The banana termination of the cable is plugged into the jack of the power supply. Okay. Next, we're going to use the multimeter. Bring in the multimeter. Okay. Connect the multimeter. Set the multimeter to measure voltage like that. Connect the multimeter in parallel with the hook. We're going to connect that in series with, that's it. With the end of the resistor, one end of the resistor and the other end of the diode. Connect the multimeter in parallel, with the positive end of the resistor and the negative end of the diode. Okay, that's what we did here to measure the total voltage. Okay, total voltage. That's what we are going to do. You start and then you invert the polarity, right? Like we did before. So you start with 10 volts, here you go. Start with 10 volts, go down to 2.8. Start, adjust the power supply from 10 volts to 2.8 volts. And measure the total voltage with the EMM. The total voltage we thought with the DMM. The DMM, okay? like that. And that then switch the polarities of the power supply and repeat step 6. Okay, so we can go back to our, here you go, that's what we did. Voltage supplied by the power supply, 10, 8, 6, 4, and 2.8. Invert the polarity, you're gonna get minus 2.8, minus 4, 6, 8, minus 10, right? And measure this voltage here, which is gonna be very close to what you read from the power supply. Okay? Next. Not this one. What's going on here? Oh, this one here. Okay. In the next step, okay, in the next step, we are going to measure the voltage across the resistor 1. Okay. That's what the voltmeter is connected here. Connect DMM. Connect DMM in parallel with R1. Repeat steps 6 and 7 with R1 to measure what I call V1. And that what we have here you go, V1, right? Repeat step 6 and 7. That's what we have here. And then next, what's left? Connect the voltmeter in parallel with the LED, right? Invert polarity, and now, okay, that's the first configuration, that's the second configuration, and the third configuration is connect the voltmeter in parallel with the, hey, sorry, it's not R1 here, it's RD. Something missing. This one is R1, this one is RD. Okay, I call it RD. Okay, so connect DMM in parallel with the LED and measure VD. VD. Like that. Repeat steps 6 and 7. When you do that, you are going to have this other column done. Okay? Data, 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 data. And then I have this result and this result, right? This result is going to be what? V1 plus VD. V1 plus VD should be close to V total and V sub. Okay? And finally, connect, adjust the DMM to read current. That's the first step. Adjust DMM to read current. Connect DMM in series with the resistor and the LED. Right in here. Power supply, DMM, resistor, LED, close the circuit. And now we're going to measure the current. The last column, the last set of measurements. And then, repeat steps 6 and 7, right? So connect the NMM in series with the resistor and the LED, repeat steps 6 and 7. And here what you're going to have, you're going to have the V divided by I, the V of the diode divided by I. You can see clearly that those numbers here are not the same, right? And when you invert the polarity, you are going to end up a division by 0, an infinite resistance. That's what it is. And you can see here is 200, here's approximately 300, 500, 800, here's approximately 2000, right? You can see that this diode clearly does not obey Ohm's law because the resistance is not constant. Okay, and that's what we have. What you have to do. You gotta plot I in the vertical and VD in the horizontal. Okay, VD in the horizontal. Note, see that because the LED doesn't let the current pass in the other direction, right? Whenever it's in the negative direction. Note, see that the voltage across the resistor is going to be 0 because all the voltage is being sucked by the diode. Okay, this voltage here is going to be similar to this voltage here. This voltage here is similar to this voltage, and so on. That's what the LED do. We do have conservation of energy, right? Because we have conservation of energy, this value here of the voltage is going to be 0. So we start plotting I in the vertical, VD in the horizontal. In order, insert chart. Here you go. Look what we get. I still right now what I have V in the vertical, right? And I in the horizontal. So I have to switch the axis. Here is going to be I. Here's going to be I. Yeah. Here's going to be G. Here's going to be G. Okay. When we do that, we invert the graph. And you can see that we have a negative voltage here. For negative voltage, we have 0 current because the LED doesn't let current flow. This, this vertical axis is I, the horizontal axis is V. That's how we usually plot the graphs for diodes. Instead of plotting VI, we plot IV. Okay. And you can see that the current increases very fast, right? It's almost an exponential increase. 10:49. Let's go another 10 minutes. So I want you all start plotting this graph. Don't forget to label the axis and put the units there. I want to make sure that you see there. Let's see. Let me crop it a little bit. Yeah. So you can see more clearly that there is indeed an increase, right, in the current. Not just an increase, is that I can do it even better than that. Let's see, I can go. I'm doing that just for you to see the feature of this curve, okay? We can get that at what? Access options. -4. 150. 150 to 200. What happened here? Let's see, isn't that, no, it's not 150, it's 1, okay. 1.5 to 2, okay. 1.5 to 2. Okay, now do you see how it grows? Right? Let's see if I can get it 1.8. Oh, too much. 1.5, 1.7, let's see. Yeah, 1, 2, 3, 4, no, it's 2. 1.6, let's do 1.6. Oh, 1, 2, 3, 4, 5. I have only 5 points here. Let's see, yeah, I'm supposed to have only 5 points. Okay, so it should be 1.7. Yeah, let's see, 1.8. No, has to be 1.7, otherwise. So now you can see that there is an increase in the current, right? And it's not linear. I will also 1.9. Let's see, 1.9. Yeah, 1, 2, 3, 4, 5 points. Okay, it's not a linear increase. And then let's go back to the original graph that we had. -10. Yeah, 1, 2, 3, 4 should be -12. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That's how the graph is supposed to look like. Okay, 1052. So let's see if you got your graph there. And once you steps, okay, plot I along the vertical axis and VD along the horizontal axis. Just for practice sake, also plot P1 along the vertical axis and I along the horizontal axis. Right? Going back here, because the resistor is our make device, insert part of the curve of the resistor. Let's see. Yeah, it will be linear like this one, right? Let's take a look here. Here you go. I'm gonna plot only the positive ones, and so we can see Ohm's law at play. 1032. Yeah, it's 1032. That's right. So it's not between. Sorry, folks. It's not between 30 and 100, but it's more than that. Otherwise, we are gonna burn our diode. Okay, so this slope matches the value of the resistor that we used. Okay, and if we include the rest of the graph, now I have to adjust here as well. Let's see here. DI. Yeah, okay. So we have a bunch of points here that are 0. See, I is 0, V1 is 0 as well. Okay. So we still get a value that's close to the resistor. Okay, 10:55. Let me see how you're doing there. Nine, 10. Okay, Jacqueline, did you download the spreadsheet? Are you there, Jacqueline? Yes, okay, so you did. Okay. Next is Yorgo. Did you download the spreadsheet, Yorgo?
Yeah, I'm doing it.
Okay. What about Paul? Paul Zapata. Are you there, Paul? Paul didn't answer to my roll call. Okay, I'm gonna put a star here again. He's away from his computer.
Professor, I put in the chat that I did.
Did you put in the chat? Ah, okay, yeah, I see it. Okay, so you got it. Now you have attendance here. Norberto is not here, right? Norberto, nope. Vanessa, did you download the spreadsheet, Vanessa? Yeah, okay, good. Sky, you download your spreadsheet, okay. Ashley is not here, right? And Corina is here, right? You download the spreadsheet, Corina? Yes, good. So we have 5 students. Wait a minute. Oh, we have 6 students, sorry. 6 students. And 10:57. In this meantime, go ahead and plot the 2 graphs. Okay. Oh, bye. Someone is, and let's have our break. Break. Let's do that a little bit longer. Let's, 10:57 to 11:15. Okay, 3 minutes longer. 10:58 actually. And I will pause our recording.
It's the lab 8, right, Professor? We're downloading the
That's
8.
right, lab 8.
Yeah, fine.
Okay, so you have 2 graphs here to plot. And what else do we have to do? Everything else that we have been doing, right? Next, there's this one is a simpler, is a simpler report. All you have to do is to fill up this number, and there will be no equation or R square or CL, but we do have to, fill up the units, right? Adjust the significant figures in the spreadsheet. You do have to do that. There will be no CL. There will be no CL or trend lines in this lab. Okay. We have 45 minutes to go. And let's go through each one of you. the next step here would be to plot. Oh, already put that here. Plot graphs. Jacqueline, did you plot the graphs? Oh, I need to share the screen, right? Thank you. Yeah, here you go. Thank you for reminding me. Oh, when am I gonna learn, right? So let's just go back here. Yeah, I just fill up the units, right? I still see lots of you folks not filling up the units there in the cells. Make sure that you do adjust the significance figures in the spreadsheet. There will be no CL or trend lines in this lab. And let's see. Yeah, you're working on that. That's good. And Yorgo? Doesn't look like Yorgo is here. Huh? Yeah, he left. Oh man, I'm gonna put here left. What time is that? 10, 11, 15, right? Paul Zapata, did you plot the two graphs, Paul? Yes, okay. Did you see the IV curve, by the way, that you're supposed to see? I'm even gonna show you this IV curve. Let me get there in the internet. IV current. IV, let's see. Let's see, how do I see? How do you call that? Current plot of a diode. Current voltage graph of diode. Here you go. Here you go. That's how it looks like. Okay. Okay, we are supposed to see a very small current flowing here, but my students weren't able to see that. Okay, we are supposed, what you're seeing right there is a zero. And we didn't go far enough to reach what we call a breakdown voltage. Depending if the voltage is high enough, you damage the device. And then it allows the current to pass, a very strong current to pass. My students didn't reach there. See here the symbol of the diode, in which this triangle here means the direction of flow of the current. Here's the current I, right? And we didn't see this part of the graph either, because the voltage, the current flowing was not low enough for us to see points, data points here, but we did see data points in this part of the curve, okay? This curve here is like a sigmoid, right? This type of curve. We see this type of behavior in many types of systems, not just in the diode, but there are many other types of systems out there that does not even involve current, but involve other types of things. We do see this type of behavior rather frequently in physics, okay? A NAS curve. Let's see, the sigmoid function. Here you go. Here you go, sigmoid function, like that. Okay? This is a sigmoid, but it's, switched, right? What we see out there is more like a rotated sigmoid function, okay? But it's kind of a similar behavior. This one has an asymptotic, right? An asymptotic behavior. And the other one also has an asymptotic behavior, but it has an asymptotic behavior in the vertical, not in the horizontal. So all you have to do is to invert the axis of this plot to get something similar there. But it's called S-shaped or sigmoid curve. And we see that rather frequently. Okay, right now I invented a liquid level sensor that behaves exactly like that. It behaves exactly like that. Okay. And again, I'm gonna write that down. And and like I said, we don't see the whole sigmoid curve there. We see only part of it. See that? The sigmoid curve would be like that. Okay, we don't see the data points here in this part because we didn't work at currents that are low enough to see those data points in this region. And we didn't go to a voltage that's high enough to reach breakdown, to reach the breakdown point of the circuit. And on the top of that, the multimeters that we worked on did not have enough resolution to see the small current in the negative direction that it is expected to be seen. Okay, that's the only differences here. Either lack of data point or lack of resolution of our equipment. Lack of data point here, lack of data point in this region, and the lack of resolution in the current in this region. Let's write it down. Okay. Here you go. The IV curve, I versus V curve of the diode is supposed to look like a sigmoid, type of sigmoid function. Okay. It does not look exactly like the one below. Sigmoid function, it does not look exactly as expected because of the following reasons. One, the actual sigmoid curve needs to be rotated 90 degrees, right? Or let me just assure you. Here you go. I'm going to plot it VI instead of IV, okay? Not this one. Oh, not this one. It's this one that I want. Okay, insert. Now it kind of look like the sigmoid, right? See, now it has the how do we call it? Now it has the right orientation, right? And we do not see this part here of the breakdown region, right? So the first thing that we have to do needs to be the actual sigmoid needs to be rotated 90 degrees, or in other words, need to swap the axis, the vertical axis, with the horizontal one. Okay, that's one thing. We need to swap. We need to swap the vertical axis with the horizontal one. Two, what else? Okay. The data that you are working with does not include the breakdown point of the diode, which is achieved, which is reached whenever the negative voltage is high enough to damage the device, okay? The breakdown region. And I'm going to also to put that graph there for you. Not this one right here. I like this graph, okay? I like this graph. Let's see if I can copy it. Okay. Here you go. Current voltage. No. I need to do better than that. Yeah, better. Here you go. I'm gonna put there in the notes, okay? And then I'll paste the sigmoid curve as well. Let's see, not this one. This one? Yeah, this one. The actual sigmoid, that's how the IV curve of the diode should look like. The IV or I versus V curve of the diode should look like the graph below. Okay. Okay, so here we go. I'm gonna center justify this guy. Okay. And then I'm gonna copy a sigmoid function here too, so you can. Here you go, this one. The IV curve of the diode is supposed to look like a type of sigmoid function. See below. See below, and that's the sigmoid function. It does not look like that. Sigmoid function, like that, exactly like that, because of the following rule. So the actual sigmoid needs to be rotated 90 degrees. Or in other words, we need to swap the vertical axis with the horizontal one. Okay, the data that you're working with does not include the breakdown point of the diode, which would be in the sigmoid curve, would be around here, okay? Be around here. The data you are working with, does not include the breakdown point of the diode, which is reached whenever the negative voltage is high enough to damage the device. High enough or low enough, right? Depending on your point of reference. True. And then we can talk more about here you go. The IV or I versus the curve of the diode should look like the graph below. Okay, so I should put it here, you know? The curve that you got here, the curve that you got does not look exactly that because of the following reasons. One, the data you're working with does not include data points in the region, in the breakdown region of the diode. This breakdown region is reached whenever the negative value of the voltage is high enough to damage the device. Okay. Okay. In the region between 0 and we do not see low current values in the region between 0 and VF, right? Forward voltage, because we do not see low current value in the region of 0 and VF. Because the students, because my students did not work in the region of low current, okay? But it's possible to do that. 3, we don't see the low current values in the region of positive V, okay? Between 0 and VF in the graph. Because my student did not, my student who collected the data, who collected this data, did not work in the region of low current. Okay. In the region of reverse current, we do not see low current values because the DMM does not have enough resolution. Okay. So 3 different, we didn't see that, we didn't see that, and we didn't see that, right? And now, how does it compare to the sigmoid curve? The IV current, the IV curve of the diode is very similar to that of a sigmoid function. It is very similar to that of a sigmoid function. It does not look exactly like that because the actual sigmoid function needs to be rotated. The actual sigmoid function needs to be rotated 90 degrees, or in other words, we need to swap the vertical axis with the horizontal one. Okay. So compare this figure with this other one here. Okay. In the case of the sigmoid function, it's not as steep as this one. It's more like an angle, but it's possible to have a sigmoid function that, that is almost in the vertical. It's possible to do that. It's almost like a step function. We call that a step function. And 11:36, we have time, right? Let's see. Good. Now, Norbert is not here. Vanessa, did you plot the 2 graphs, Vanessa?
I'm still working on it.
Okay, still working. Do you know how to invert the first graph, the graph of the diode? Do you know how to do that?
Yeah, I just needed help plotting it so that it makes the sigmoid line through it.
Yeah, so let's see, let's go step by step here, right? Like I did. So here you go. First, you're going to plot VD, right? And I, right? Did you do that?
Yes.
Okay. Okay. So, but that's not what I want. What you plot here is VD versus I. What I want is I versus VD, right? That's the problem that you're having, right? To invert the axis. Is that right?
I inverted it already.
Ah, you already inverted. Okay.
Yeah.
So you're done. There's nothing else that you need to do. Okay. Well, what
Oh,
was your question?
yeah, a line through it or anything?
No. There's
Okay.
no trend line whatsoever for this graph. Okay. So you managed to invert the axis, right? Just like I'm inverting here. You go
Yeah.
edit G. I'm gonna change to I here. I'm gonna change to I here. Here change to V to G. Here I'm gonna change to G. Okay. So you got that, right? So the sigmoid would be like that. But you cannot plot it like a sigmoid curve because you don't have enough data to do that. Okay. So good. So we can move forward, right? Let's see another student here. Sky, did you plot the two graphs? Let's see. Looks like Sky is not here. Yeah, she left too. Gosh, well, maybe. Okay, let's see. And Ashley is not here, right? And Corina. Hello, Corina. Yeah, you plotted both graphs? Okay, so let's work. Okay, so let's work on the units now, right? On the units right now. And then we work on the sig figs. 11:39, we have 20 minutes to go. So let's see, Jacqueline, did you manage to finish the two graphs, Jacqueline? Yes, okay, good. So we start working on the unit and sig figs, okay? And let's see, Vanessa, did you manage to finish the two graphs?
Yes.
Okay, good. So now I expect you to start working on the units. We have time for that, for you to do it, right? Let's write in here. Don't forget to put the number of data points here, right? If this is a voltage, so you gotta put the proper unit here. This is a voltage as well. This is a voltage as well. This is a voltage as well. And this is resistance, right? Let me change the numeric format. Yeah. Do you see what happens to if we use this equation? The diode doesn't have a constant resistance value. They don't have a constant resistance value. And they keep on increasing, right? They steeper. You keep increasing now, keep on decreasing. Let's see. Yeah, it keep on decreasing, right? From 3 volts to 10 volts, the ratio VD over I decreases. The same doesn't happen to the resistor. I can, I can do that for you here. See, I'm gonna get V1 divided by I is gonna be almost constant. Okay, that's gonna be R of the resistor. R1, right? V1 I. And then we go ahead. Okay, and look at those numbers here. Format cell number. See that? They're almost the same. Okay. Here in this case, V1 is 0 divided by 0. Okay. 0 divided by 0 is it's not a division by 0. It's there's a name for this type of numbers, right? It can be any number, any non-zero number. But there's a name for that when 0 is divided by 0. I will remember. But we study that in math. But note, see again, the largest percentage difference is going to be 5 units out of 100. So the largest difference in resistance values here is going to be at most 5%. At most 5%. So this is a very good ohmic element. Unlike what you see here, right? For the diode. Unlike what you see here for the diode. 1143. And let's see. Let's work on the units, right? That's the idea I came here. Here you go. You do have a unit for the resistance here as well. Okay, we do not have a value for the resistance of the diode because it changes, but you have to have units for voltage here. You have to have the unit for ohms, right? Here you have, this one is very simple, very little work. Well, the only thing that's gonna give you work is gonna be the significant figures that you see here, okay? That's what you have to work. So, and then you look at that PDF file that I gave you. So let's see, let's go through one by one now. Jacqueline, did you fill up the units? 739, yes, okay, good. And what about the sig figs? Working on it, okay. Now, Yorgo left, right? Next, Paul, did you fill up the units? Yes, okay. What about the sig figs? Looking at the table, okay, good. So you're working on that. Norberto is not here. Vanessa, did you finish the units?
Yes.
Okay, what about the sig figs?
Working on that right now.
Okay. Sky, I left you, right? Left. Ashley is not here. Corina, did you fill up the units, Corina? Just the units, okay. And now you're working on the sig figs, right? Yeah, okay. I'll give you a little bit more of time. I stop sharing the screen momentarily and wait a little bit. Let me know if you have any troubles with the significant figures, okay? I'm here to help you. Let's see, someone, if the number is zero, so yeah, you don't worry about it. If the number is zero, you don't do anything with it. Yeah, there is no significant figures for zero, right? $11.49. Oh, right. Oh, left. Yeah. This one. Did I write that down? Lab 8 due on, yeah, don't forget the next one. Okay, lab 8 due on the 22nd. It's here. Now, is anybody finished the sig fix? Take this opportunity to work the sig figs, right? So you can get a better grade in this lab. Okay. So let's go back here. Jacqueline, did you manage to work on your sig fix? Did you manage to finish, right, your sig fix? Almost done. Okay, that's good. Almost. And Paul, did you manage to finish your sig fix? Almost done too. Vanessa?
Yes.
Yes, okay, so Okay, so if you wanna leave, you can leave unless you have any questions, right? Okay, and Corina, did you manage to finish your sig figs? Yes? Okay. Well, I guess we're done for the day, right? So it's just all you need is spend some time working with that. It's not a difficult concept. Those are the sig figs, but you have sit down and spend some time. What I like to tell my students is that we are teaching not just physics here, right? We are teaching something else too. Well, we're teaching what people call discipline, right? What we call discipline, and discipline has this bad reputation, right? Because of the disciplinarians that used to punish the students, right? I don't like, it's the word discipline, right? Has this bad reputation because of that, right? But that's not how I see discipline, okay? I see the practice of training people to obey rules or a code of behavior using punishment. I completely disagree with this definition of discipline. I completely disagree, okay? Discipline is actually the process of training someone to do something in an automatic fashion, okay? And that's very important when you're becoming a professional, to do something, difficult automatically, okay? That's how the definition of discipline that I like to tell my students. We're not punishing you for you to develop discipline. No, we are making you do this many tasks over and over again, so you can develop this discipline, or so you can develop this habit of doing something automatically as a second. There's a name for that. The second nature, right? It's just like walking, right? Just like walking. Think about a little baby. When we were a little baby, we didn't know how to walk. But after practicing so many times, we managed to learn how to walk without thinking. We managed to learn how to walk as something that comes automatically to us, right? And that's what we are doing here in this course, not just teaching physics, but teaching you folks to learn physics and math, so all of that becomes second nature to you, okay? And that's the message I want to give you, okay, about discipline, okay? And I hope you all agree with me. I don't think discipline should be something bad that we use punishment to correct the disobedience. No, that's not what it is. Discipline for me. Okay, discipline is the act of training someone to do something difficult in an automatic fashion, automatically as second nature. Okay, so we can stop now, right? And then I see you when Monday, next Monday. Okay, and by the way, I have office hours right now too until 12:45. If you want to join, stay around. Otherwise, I will see you on Monday. Thank you for being here. Thank you. Thank you, Vanessa.
See ya.